Here's some comments and solutions for the graded homework. See if I can do this without coughing too much. Sine x plus y was the function, and we wanted to know what do the contours look like and what does the gradient look like. Well, the computer does the gradient for me. And the contours, the thing that a lot of people were having trouble with, is remember if it's a function of only x plus y, then if you set that equal to a constant, you're going to get things of the form x plus y equals some number. And so those are all lines parallel to y equals minus x. And so they're lines in the north-west southeast direction. And you can see that the gradient field is perpendicular to that. Now, I didn't worry too much about the details, but to be a really good picture of the gradient, you should have some of the arrows be rather long, going upward, like sine is increasing as you go through 0 and going up to the right, up and to the right. And that's increasing pretty strongly. Then it increases less strongly, and then of course it starts decreasing. So the gradient arrow actually points backward, and then it starts getting even stronger backwards, less backwards, and then flips again. And so they keep flipping back and forth. And people got that, but to be a really good picture, you want the size of those arrows to change as well. Okay. But again, this idea, if you have f of x plus y, or f of any linear function, the contour plot is actually going to be very simple. It's going to be a bunch of parallel lines. It's the values that are attached to that lines that depends on this outer function, the sine function. So that's all I wanted to say about that problem. The next one was the integral along a curve, which was two straight lines of this function plus c squared. Okay, so that's a vector line integral. It's written in the differential form notation, but we can always think of that as f dot dr. Make those into vectors, where f, is the vector field x squared I plus y squared j plus c squared k. Okay, so how do we do that? Well, because c is two separate pieces, we have to do it separately. So let's call it integral over like c1 of all this stuff. Oops. That's not working. Okay, plus integral over the c2. That's the second straight line. And for each one of those, we're going to parameterize it. Well, let's see. What's c1? That is going from 0, 0, 0 to 1, 2, minus 1. And c2 is going from 1, 2, minus 1 to 3, 2, 0. Okay. So we need to parameterize these guys. Well, this can be x, y, z equals just t 2t minus t. That'll work. Here, it's a little more general. Okay. We're going to want it to go from 1 to 3, 2 to 2, minus 1 to 0. Oh, I need a comma there. Okay. So remember, we can always parameterize it as t times the destination point plus 1 minus t times the origination point. That's going to be a straight line because it's linear, and when t equals 0, you're going to default to the origination, and when t is 1, you get to the destination. Or in other words, let's see if I can fit it in here, that's going to be 3t plus 1 minus t, so 1 plus 2t. And then, of course, the 2 is constant, so you just get 2 with the t's cancel. And then we just get t minus 1. Okay, and so let's just double check if I did the arithmetic right. When t equals 0, I get 1, 2 minus 1. That's correct. And when t is 1, I get 3, 2, 0. Yep. Okay. So remember, we need more on these things. We need x prime, y prime, z prime. We need the velocity vector. And this is what people were having trouble with. Okay. Here it's really easy. It's just 1, 2 minus 1. And then here, once we've got this simplified form, x prime, y prime, z prime is just going to be 2, 0, 1. Okay. So now we're finally ready to go back up into here and do those for real. So this is going to be the integral. Let's see. T is just going to go from 0 to 1 here. And I convert everything in here. So x squared is going to get converted, so that's going to be t squared. And remember, dx turns into dx dt times dt. Now, that happens to be just dt here. Y squared is going to be 4t squared times dy is now going to be 2 dt, because dy is y prime, which is dy dt, which is 2 times dt. So times 2 dt. I guess I'll put in a little dot there. Dot, okay. Plus z squared is minus t quantity squared, so you just get t squared, times minus dt. So I'll put in a... Okay. And then similarly for the next one, let's see if we can just copy and paste. Change everything accordingly. X squared is now 1 plus 2t quantity squared. Now that's a 2 dt, because this is a 2. The dy just dies completely. And then t minus 1, that's z now, quantity squared. And here it's dz dt is 1, so dz really is equal to dt. Okay. Now you can just factor out the dt, and you've got an ordinary integral. And I won't bother to finish it up. Okay. But what people were missing is that dx, dy, and dz have to be converted to dt through dx, like dx equals, this is, what am I using here? Let me just make clear what I'm using here. dx is dx dt times dt. dy is dy dt times dt and dz. Okay. So that's that was a crucial piece that was missing. Okay, then the last one, people had enough trouble with it that I didn't grade it, but I want to look at it. We've got a helix. It's not quite our standard helix. It's going off in the x direction, but that's okay. Okay, and it's one full cycle. So t is between 0 and 2 pi. Okay. And we've got a density. And of course, this unfortunately, this silly... well, since it's the linear density, we can call it lambda. We don't have to use rho. And it's equal to the square of the distance from the origin. Okay. So, we want to find, for example, the mass. Well, the mass is the integral over the curve of the density ds. Okay, because this density is supposed to be mass per unit length times a little bit of length. That's really dm. That's a little bit of mass. And then you integrate it and you get the total mass. Okay, that's a scalar line integral, so that's one thing. People were treating this as a vector line integral. They're very different beasts. This is a scalar line integral. There's no flows, there's no fluids, there's no forces. It's just scalars adding up, little bits of density adding up. But now we've got to parameterize that. Okay, well, they've given us the parameterization. That's actually nice. Okay, lambda is x squared plus y squared plus z squared, so we'll put that in. And then one thing people were missing is cosine squared plus sine squared is 1, so that's actually not too bad at all. Okay, and then ds, okay, well that's ds dt times dt, that is the magnitude of r prime of t. Make sure we know that's a vector, times dt. Okay, so really right when we get our parameterization, right when we get our parameterization, we should go ahead and calculate the velocity. Okay, and so x prime, y prime, z prime equals, not too hard, that's 1 minus sine t cosine t. But remember, all we care about is the speed, which is the magnitude of that guy, and that's going to be root 2. Because again, sine squared plus cosine squared equals 1, plus 1 is 2, inside the square root is root 2. And so that is what goes in here. This is the speed right here, and so that's going to be, the root 2 comes out, and we just get the integral from 0 to 2 pi of t squared plus 1 dt. And that's not really that hard. Okay. Now what about the center of mass? Like x bar, for example. Let's bar this thing. Come on. X bar, that's going to be the integral over the curve of lambda times x ds. This is talked about on page 1036. We did examples of this, so I was a little surprised that people had this much trouble with it, but maybe it's because it's three-dimensional. It's not any different. It's just x times the density. They use rho, but I think that's silly for a linear density. Lambda's a better letter. So, what's that going to be? It's going to be very much the same setup. Okay, I've got less than 3 minutes left on the screencast here. Okay, so we got the t squared plus 1 is still the density. Then we've got x is t, and then we've still got the root 2 dt. Okay. So, oh, and then of course it's 1 over m times that. I got distracted here. Okay. We always got to divide by the mass. So that's something calculated above. That's not too bad. The one that is harder is like y bar. So a lot of people were asserting, or a number of people were asserting, that they thought y bar and z bar should be 0 because of the symmetry of the situation. That would be true if the density was constant. Remember, symmetry for an integral is always what's the set you're integrating over and what's your integrand, and they have to both have some symmetry. Here, that distance, this density being equal to the square of the distance from the origin, that behaves in a somewhat complicated way as you go around that one cycle, and it doesn't turn out to be 0. Okay, so 1 over m integral 0 to 2 pi. Okay, so now you get t squared plus 1, and then like cosine t times root 2 dt. Okay, so you're going to have to do integration by parts twice to do t squared cosine t. Now, the 1 cosine t, I have to say, integral over one full period of cosine or sine, that dies. And so it's not as if it's as if that isn't even there. It's not a huge simplification, but it helps. And then that's not the world's hardest integration by parts problem, is to do t squared cosine t. Then z bar is t squared sine t. The answers you get are pretty random. They have lots of weird pi's and stuff like that. Pi's and root 2's and various fractions. But they're manageable.